addressing a range of industries and technologies because counterfeiting is an enormous business, bigger at the moment than 3D printing, and it affects the full range of company issues. Not only does it affect profits, now this is as an American I put up the US issue, but it's $1 trillion business worldwide. It erodes customer confidence in your product, and furthermore, buying from counterfeiters can support terrorism and organized crime networks. And 3D scanning and 3D printing makes it extremely easy on the counterfeiter. So we're enabling at the same time that we begin to worry about the integrity of our own products. What InfraTrac does is light-based verification. So we place a chemical fingerprint invisible layer into the 3D printed object. The detector is a spectrometer. In the case of polymers, it's pocket-sized. In the case of metals, it's a bit bigger, but it's still a handheld, off-the-shelf instrument that makes it easy to do fast and easy yes or no authentication anywhere in the field. It's a non-destructive technique, so that means that if you don't trust the paperwork of the guy before you, you can simply say, let's check that again. And that's why it's been called the most promising and amazing technology, because when you have the problem of counterfeiting and you need to think of a way to validate with 3D printing, chemical options serve the purpose. Additive manufacturing intellectual property protection, you can use licensed taggants. Gartner says 3D printing intellectual property theft is going to be over $100 billion business by 2018. That's probably a ridiculous exaggeration, but the fact is it's a big problem and it's growing. It's already a problem in every one of the industries that additive manufacturing serves. That is, supply chain security is already an issue across all of those industries. And 3D printing just makes it worse and makes it easier. As with the rise of production quality additive manufacturing as a whole, defense and aerospace are the first reasonable markets where it's important enough to be able to do it. Automotive, transportation, trucking, and so on, and medical devices are also of importance, as they are in the production development of additive manufacturing. So how do we do it? This is a peanut butter and jelly sandwich. I apologize to those in the audience who have not ever tasted peanut butter and jelly. It's a perfectly good sandwich, but in this case, I'm using it as a metaphor. You're welcome to think of jam and butter or whatever's the appropriate sandwich here. So we place the chemical taggants layered into the product as if in a sandwich. It doesn't need to go all the way to the edges, because then you could peek at the edges and see what it is. It can just be a little spot. It can be a tiny little spot. So we choose compatible chemicals and layer them in a hidden way inside. And we choose on the basis of material compatibility and whether they can be detected with a spectrometer. And the detection can just be done anywhere, so that the brand protection that's already in place in all of those supply chains, or new brand protection, can do its job in a faster, smarter way. And it's cost effective, but it also uses some of the return on investment from being able to save money on the forensic work you would otherwise have to do to answer the question, if this hurt somebody or if this caused a failure, was it because we did a bad job, or because somehow in the supply chain someone else got their materials or their part into our supply chain? That is, whose fault really was this? And that forensic work is already being done and already costing lots of money. This is a fast way to make that work faster, cheaper, and more targeted. So in the case of polymers, if you look at a white plastic, you can say, well, so what is that? It looks like white plastic to me. In the view of the spectrometer, though, white plastic isn't just white plastic, it's a chemical analyzer that can tell all those plastics apart. So that is just a stratasys ring of different polymers, and the spectrometer can tell them all apart by looking in the near infrared region. So what does that mean? Infrared, that's the part where heat is. Visible region is what your eye sees. So in this slide, the graph with the rainbow under it is what your eye sees because it's visible light. And all of the samples of the same material in different colors pattern differently. So you can see that the red lines are all different in the rainbow graph. But in the other graph, in the near infrared region, color isn't important, but material is. So the samples that are made of the same color but different materials can be detected by the spectrometer. That is, in the visible region, in the rainbow part where your eye sees, all the whites and all the beiges look the same, but you can see the different colors. In the near infrared region, this is what the spectrometer sees, and I'll tell you in a minute that nobody who's doing the testing ever has to know this. I'm just showing you to help you understand how we do what we do. In the near infrared region, all those different polymers, even if they're white and beige, show up as different curves in the graph. So you can see materials as if you had supervision when you're using the near infrared spectrometer. For metals, and again, the user has a point and shoot device that gives you a yes, no, red light, green light. Does it match? Does it not match? I'm simply explaining what's under there so you can see the technique that we're using to make this chemical fingerprinting work. For metals, these are tagged samples printed with the assistance of the research team at Penn State University on an Optimec DED printer. So we're using a chemical fingerprint, and you think for a moment, well, how are you sticking that extra peanut butter and jelly sample in there? Well, it certainly is easier if we use multi-material capability printers. For metal, DED offers that option. We used an Optimec because it has 2 feeders, and the presence of that additional feeder makes it possible for us to sneak our peanut butter and jelly, in this case consisting of a different metal alloy, into that part as it's made. Then we sent it to a separate lab that didn't know what we'd put on or where we'd put it, and they played find the taggant by mapping a little grid onto it and trying to find the tiny little spot where the taggant was, because by looking at it you can't tell. That's the real genius of the covert fingerprinting. So they created this matrix, and using an X-ray fluorescence spectroscopy to find it, they managed to find in yellow highlight the parts that have different material in those little tiny spots. So if you think of this from the standpoint of a counterfeiter who's trying to figure out, is this a tagged part? And where did they put that tag in? And what's that tag in? Oh, I'm a smart counterfeiter. I'm going to get my own spectrometer and I'm going to test every centimeter of that thing. Well, it's going to take a long time because only the spot that's got the tag in it is going to yield to you. So even the most determined of counterfeiters, wise to the technique and able to use the spectrometer, still is going to have a heck of a time figuring out where the tagging is, what it is, and then being able to replicate a part that is similarly tagged is actually a major challenge within the chemical technique. Then your next question might be, well, but we're going to polish that part. Aren't we going to polish your taggant right off? So we tested that, and the answer is it's slightly affected, but nope, it's still there, and there's no problem at all. So what are the other ways that you can use to protect 3D printed parts or materials? Well, certainly it's important to have some form of cybersecurity so nobody steals the design file. And there's certainly are ways that you can protect that. You can make the print usable only one time, for example. But as you come to realize, once you're using a cybersecurity solution for your additive manufacturing, eventually the file is over here and the part is over there, and the protections you put on the file aren't doing the part any good at all in the supply chain. So that's why a chemical solution gives you an additional layer of traceability and authenticatability. There's some discussion of the potential use of quantum dots, which is another chemical tagging technique with essentially molecules that advertise their presence quite loudly, so to speak. But the ones that do that best don't scale up very well. They tend to come from countries you might not want to trade with in your security system, if you're worrying about security. And furthermore, the ones that work best are based on cadmium and lead, and you don't necessarily want cadmium and lead in your product. Another solution potentially available for security tagging that also uses a chemical approach is to use DNA. In this case, not DNA as a metaphor, but literally DNA, say, derived from botanical sources. But one, in order to do the validation, you don't just point and shoot with a handheld off-the-shelf device. You pretty much have to sequence the DNA, which is not really a field test at all. And furthermore, DNA fries. In almost every one of the currently viable additive manufacturing processes, the heat is too high for DNA really to be any use at all. And certainly in metals, you'll just cook it. We have been working with a cybersecurity partner because it really does make sense to protect the file. So Identify 3D has a way to do essentially digital asset management on the file itself. So we feed into it at the design stage. So in order to determine essentially where you put the peanut butter and jelly into your sandwich, InfraTrac provides a file for encryption that feeds into the print file. So a little snippet basically of G-code or the like that tells it, the printer, put this spot of this material in this place. It's encrypted, so we're not advertising what goes where. And then that will be available for validation in the field with the handheld light, the spectrometer. Furthermore, at the manufacturing phase, you can add extra security by doing a handshake with the firmware in the printer. So you can say, when we work with Stratasys firmware determines that there is, as expected, the correct snippet of InfraTrac code and that it is using the correct material. All is valid. Go ahead. You can make the correct Stratasys validate in the field multi-material part with hidden InfraTrac tagging. And then, of course, in the field, the spectrometer gets the data that enables a nearly idiot-proof yes-no, point and shoot. The Polymer instrument is smaller than this, that lets anybody from a loading dock on to answer the question, did you check this? Do we really trust this? Is it safe to use this additively manufactured product, even though the paperwork may look good? You don't know if the person who signed that paperwork last had to his head. So you want to make sure that before you use it in your high importance application, aircraft, automotive, medical devices, and beyond. You made sure that it's absolutely legitimate. As prototyping moves to production, the initial view of security is, hey, we're not going to have a supply chain at all because the printer is going to be right next to me. Why do I have to worry about that? But as you can see by walking outside onto the show floor for even 1 minute, you realize that the multitude of printers that you can use and will probably need to solve all challenges mean that right next to all of them at all, you're still going to have a supply chain. And once you have that supply chain, then the safety of your parts is critical. Let me anticipate a couple of questions about the safety of the tagging itself. I often get a question, how do you know when you put that little spot of so-called peanut butter and jelly in there? No, it's not really made of jelly, but when you put that in there, how do I know you didn't cause strain in some place that's going to cause the part to fail? So we are using industrial quality materials as our taggants. We make sure in collaboration with the manufacturer that they are compatible and are not going to compromise the strength of the material itself. Moog is an aircraft parts manufacturer we work with, and they are using the same algorithms that they would normally use to decide where to put the label, to decide what are the good places, what are the safe places where you can add tagging. Because already they've thought about the problem of, well, you can't put the label in a way that will weaken the part. And those are really the same calculations that we use as well. So you can build the protection right into the file and in as a chemical fingerprint. Let me take this opportunity to mention that beyond aerospace and defense, beyond transportation, into medical devices, it is possible even to print drugs. So if you're printing tablets and capsules, you want to make sure that you're not getting just some junk that somebody printed in the garage for you, right? So InfraTrac has ways to tag those as well. If you want to see an example of printed drugs, the startup section, which is that way, has a booth at FabRx, F-A-B-R-X, and they have on display 3D printed drugs. And in our previous work, we came out of a pharmaceutical taggant industry to begin with, and so the taggants there are edible, compatible, layered right in there like peanut butter and jelly, and in that case, closer to actual peanut butter and jelly because safe, drug-related, and safe to eat. Among our partners, America Makes funds the shift in additive manufacturing from prototyping into industrial production. And then we are working with, as I mentioned, aircraft players like Moog, a supplier to Lockheed Martin. Deloitte is a worldwide consulting company that has made real inroads in thinking through what is a digital twin, what are the things you need to keep track of, how do you manage the process of making sure that production is optimized in this new world of 3D printing. With ChemCubed, we've made a new kind of tagged samples. They do jettable nanocomposites, so high-end materials that are compatible with space as well as medical devices, and then the printer companies you can see as well. As a test, if you need to show that you have done your best, and that the reason that something has failed is that it sneaked your supply chain. This is a non-destructive test. It can be repeated, and it's always nicer to be able to repeat it in front of a judge and jury, to be able to say, look, this thing is fake and I can prove it to you. It looks the same, but we can tell that it didn't have the correct InfraTrac chemical fingerprint on it, and therefore it sneaked into the supply chain. It's a dangerous part. Spectroscopy as a science is backed by over 70 years of work. It's the forensic tool of choice for figuring out, so what was that thing made of and how was it made? In the polymer arena, it detects moisture and particle size, so it serves in addition as a kind of extra quality check. In metals, X-ray fluorescence spectroscopy does some of those things. It's a bit sensitive to particle size, but not quite as much. As a technique, it's never been reverse engineered. You can ask me afterwards. The details are a little bit technical, but you can't just say, hey, I have a spectrometer, I can figure out how you did that and make my own. No one has ever done that, and you just can't do it. The science doesn't allow it because the peaks move each other. So you can't just say, I know what that peak is, I'll look it up. Looking it up doesn't help because it's in the context of the matrix material, therefore you can't do that. What the tester has in her or his hand is a little spectrometer, and it has a yes-no answer, but behind that is a complex chemical statistics model, a chemometric model that figures out what counts as a match. So there's smarts in it, but they aren't required by the end user. It's also possible to tag electronics. As you'll see, there's a lot of exciting work in creating printed circuit boards, and you can see it from companies like Nano Dimension here. And that means that you can print in flexibles and wearables that are internet enabled, that are part of the Internet of Things. And in all of those cases, we can tag right into there as well. So we can be layered right into the substrate and part of that printed circuit board, so you can check it with the same light and tell, yeah, but is this real? Because it begins to really to matter. There's also an after-coating option, so instead of layering the peanut butter and jelly inside the sandwich, on as a covert protective layer. Multiple options for that technique include ultraviolet cured films, and there are after layer coating options. So for example, you could print on a powder bed metals printer and then place it into a DED, a directed energy deposition type printer, for a tagging layer after that. How do you start? Well, you can tag at production or as an after layer. And really the question is, what do you want to tag? What's vulnerable to counterfeiting? What's high importance? It's a cost-effective method. It scales well, but you still need to decide what it is you want to tag. We charge by a license and a royalty fee, so it's easy to get started. The match model InfraTrac creates so that the person in the field can tell, yeah, yes or no. And the idea is for us to fit into the existing supply chain infrastructure so that what's being checked is selected on the basis of the best science, rather than, oh, we'll just take some random samples and send them back to the lab for expensive testing. It's much smarter to do that first layer of quick testing and choose the really dodgy samples and send those back for the test. Great, well, thank you.